Okay, the next section is calculating the equilibrium concentrations. So this is the third use of the equilibrium constant. In these type of problems, you're given the equilibrium constant and the initial concentrations, and the equilibrium concentrations of all of the reactants and products can be calculated. There are two types. There's the simple, which you can take the square root of both sides, which means both the numerator and denominator must be squared, or the second type, which I actually prefer, is actually the quadratic. I think it's a little simpler in reality, but I'll show you an example of the first type, the simple type. So this is number 68 out of the Ebbing and Gammon book. It says initially a mixture contains 0.795 moles of each nitrogen and oxygen in an 8-liter flask. So I have things like I have a volume of 8.00 liters. I have a temperature of 3,900 degrees C, and I have a Kc value of 0.0123. Okay. So we're going to do this like we started out doing the initial problems at the beginning of this chapter, which is we have a balanced equation, and I'm going to need all the white space on this slide that I can get, so I'm just going to write underneath this. So I have an I, and I put down 0.795 moles for both nitrogen and for oxygen. And it doesn't tell me how much NO, so that's going to be 0. The difference between this problem and what we did initially was we could work the problem in moles, and then before we put it into the Kc expression, we could change it to molarity. In these problems, they need to be in molarity initially. So I'm going to add another row here of Im, in which I'm basically going to change these to molarity by dividing by the volume all the way across. So when I do that, I get 0.09938 molar, 0.09938 molar, and of course 0 molar. Then I do the rest of it like I would normally do it. The change, this is a reactant, so it's minus X. This is a reactant, so it's minus X. And this is a product and has a coefficient of 2, so this is 2X. And what I'm looking to calculate is the E. I don't have anything. I wasn't given any value at equilibrium. So my Kc expression for this, my equilibrium constant expression, is going to be the concentration of NO squared over N2 times O2. So when I start putting in numbers, I have 0.0123 is equal to 2x squared over this 0.09938 minus x. That's my nitrogen. So basically I'm doing what I did before where I used I plus or minus C is equal to E. Well, I don't have any E values, so I'm basically putting in the I plus or minus C into this equation. I dropped the 0 because it doesn't change this. It would be technically 0 plus 2x squared, but I dropped the 0 because it doesn't change it any. And so this is the nitrogen. The oxygen is the same thing. Because of my starting amounts were exactly the same, therefore this times that is basically the same thing as saying it's squared. So 0.123 is equal to 2x squared over 0.09938 minus x squared. So I can do what they call the simple form because both my numerator and my denominator are squared. So what I'm going to do is I'm going to take the square root of 0.0123 and the square root of this whole side, 2x squared, over 0.09938 minus x squared. When I take the square root of a number, I get either the positive value or the negative value. And so I get a positive 0 plus or minus 0.1109. When I take the square root on this side, I just get rid of the squared sign. So it's going to be 2x over 0.09938 8 minus x. Okay? To me, this is where it gets complicated, and I really don't prefer this method. But I'm going to go to the next slide because, as you see, I ran out of room on this side. So I'm going to start from here, and I'll rewrite that on the next slide and show you what we need to do next. So from the previous slide, I had plus or minus 0.1109 is equal to 2x over 0.09938 minus x. So I need to do both the positive value and the negative value for this. So to me, this is actually longer, and I'm going to show you the other way in a few minutes. So doing the positive 0.1109, I get 0.1109 is equal to 2x over 0.09938 minus x. So to solve this, I need to multiply through by both sides by this. So I get 0.1109 times 0.09938 minus x is equal to 2x. Now I need to distribute, so 0.1109 times this gives me 0.01102. Distribute this times the x gives me 0.1109x is equal to 2x. Now we'll combine like terms, and I'm going to do that by moving this term to the other side by adding on both sides. So 0.1102 is equal to 2x plus 0.1109x. So I get 0.1102 is equal to 2.1109x. Divide both sides by this 2.1109, so I get 0.1102 divided by 2.1109 is equal to x, and x then ends up being 0.00522. Okay? I have to do the same thing for the negative version of this. So I have a negative 0.1109. Probably the easiest way is the fact that none of these numbers are going to change, just the signs are going to be changing. So I have a negative 0.1109 is equal to 2x over this 0.09938 minus 2x. Oops, minus x. Not 2x, minus x. So now I do the same thing where I multiply through, except for this one's a negative 0.1109 times 0.09938 minus x is equal to 2x. So basically I'm going to end up with the same line here, except for the signs are going to have been flipped. So I don't have to redo the math. It's 0.01102 plus 0.1109x is equal to 2x. Now my numbers change again because I'm going to subtract this to both sides. So I get a negative 0.1102 is equal to 2x minus the 0.1109x. So I get negative 0.01102 is equal to 1.999x. So negative 0.01102 divided by 1.999 is equal to x, and x ends up being a negative 0.00551. I can't have a negative x. So that means that this calculation is not the one I use. I'm going to use instead this one right here. So I'm going to go back to my previous slide now and get my final answer using this 0.00522. So I'll write down here at the bottom that x is equal to 0.00522. And now I'm going to do this once because it's the same calculation here. So for these two, it's 0.09938 minus the 0.00522. And so for this, I get 0.0942. I'm going to want three significant figures, and the units are molarity. The oxygen is going to be the same value, 0.0942 molar. So even if it's the same answer, I want you to write it down twice. And then this is going to be 2 times that 0.00522 to give me 0.0104 molar. And so my final answer are these three answers right here. And so that's the simple form. On the next video, I'm going to show you this using the quadratic formula, which is personally my favorite, but I did want to show you this way of doing it.